The rule for scientific notation is that this value, this m value, has to be greater than 1, but not greater than 10. So that number needs to be between 1 and 10. That's super important. This number in scientific notation needs to be between 1 and 10. Okay. Always, always, always. So does this work in scientific notation? 30 times 10 to the second. No, all right? It's not between 1 and 10. Does not work. What about this? 0.4 times 10 to the negative second. No, not between 1 and 10. So neither of those are valid options for scientific notation. Okay? What scientific notation does is allows us to express values that are either very large or very small with more flexibility. Okay, so scientific notation allows us to view very big and very small numbers, right? Just in a little bit more reasonable format. Sometimes when you teach scientific notation, you talk about what way you move the decimal and all that kind of stuff. I don't teach scientific notation that way. What I'm going to do is we're going to look at our original number. So let's say I have the value that's my original number, 1,256,000,000. That's my number. And I want to express that in scientific notation. Okay, so what we look at is we take where our original decimal place is, which is here. Our new decimal place in scientific notation needs to be in the ones place, so right there, right? And I have to move it to get from my original place to my new decimal place. I had to move it 1, 2, 3, 4, 5, 6, 7, 8, 9 times. I don't want you to memorize move it left is positive, move it right is negative. I don't like that because I could have just as easily went like this. 1, 2, 3, 4, 5, 6, 7, 8, 9. The way I want you to understand it is I'm going to write 1.256 times 10 to the 9th. And my exponent is positive because my original number was greater than 10. That's all I have to look at. My original number was greater than 10, so my exponent is a positive 9. Right? I don't want you to have to think about if I move it left, it's whatever. If I move it right, it's whatever. I just want you to think about the original number I was trying to express was greater than 10, so my exponent is positive. Okay? The same would be true for smaller numbers. Okay? This value is less than 1, which means my exponent's probably going to be negative. So I have to move. What two digits does my decimal place need to be between? It needs to be between the 6 and the 2 because that puts my number between 1 and 10. So 1, 2, 3, 4, 5, 6 places. So 6.2 times 10 to the negative 6. Right? Because my original number is less than 1. Okay? So let's practice a couple. I want you to write this number for me. 1.43 times 10 to the 3rd and 1.43 times 10 to the negative 1st. I want you to write both of those numbers for me. Expand those out of scientific notation and write them in their full value. This number is a tiny bit different because it shows you your original decimal place. Right? It shows you where your original decimal place is. Here's my original. Here's where I need it to get to. So our answer should have been 1.3 times 10 to the what? Second. Times 10 to the second. A lot of you want to do this. 1, 2, and move it all the way to the end of the numbers. That's not the case. Right? The number is 134.6. 6892. Right? The number is not 134 million. The number is 134. We only had to move it 2 places. Original decimal to where we want our decimal to be. Okay, that can be a little bit tricky, so I want you to feel comfortable with that. Does that part make sense? Okay. Now we're going to move on to something called significant figures. Significant figures. Or you'll hear me call them Sig Figs. Sig Figs. What does significant mean? Major or important. Good. Significant figures. Significant figures tell us what digits in a measurement are important. What digits or numbers in a measurement are important. Okay, not all of the digits that we see in measurements are important, believe it or not. Okay. So I just want you to walk through this example. You do not have to write down this second bullet in this example. I want you to just listen to what's happening here. All right? I want you to just listen. In as 14.3, I know for sure my measurement is between 14 and 15. Would we agree with that? And then the 3 value has been what? Estimated, right? I estimated the 3. Okay, so I put thought into each and every one of those numbers, right? I put thought into each of those numbers. I know it's between 14 and 15, and I thought that it's about the 0.3. So each of those digits is what we consider significant. Each of them is significant, okay, because I put thought into each one. 3 valid digits, 2 that I'm sure of, and 1 that I estimated. Okay, so I'm going to give you this whole list of rules for significant figures, and then we're going to talk through examples for each of the rule. Okay, so I'm going to give you time to write them down, and we're going to go through examples. So the first rule for significant figures is any digit that is not a 0 is significant, because we don't throw around 7s for no reason, right? We don't throw around any other digit for no reason. Zeros is where significant figures gets a little different. Okay, but any digit that's not a 0 we consider significant or important in our measurement. Okay, any non-zero digit is significant. So if I have 164 grams, how many sig figs? 3. If I have 8 pounds, how many sig figs? 1. Okay, good. Easy enough. Second, all zeros, right? Most of our rules are going to revolve around zeros. All zeros to the right of digits after a decimal point are significant. All zeros to the right of digits after a decimal point are significant. Okay, these zeros are to the right of digits, and they're after the decimal point. What they tell us is that we think it's 13, and we think it's exactly 13.0. Okay, that zeros to the right of digits after a decimal point tells us we think it's exactly 13.00. Okay, so how many sig figs here? 4. The 1 and the 3 are significant. Both zeros are significant because they're to the right of the decimal place after digits. That's super important. What if I had a measurement that was like this? 17.510. How many sig figs? 1, 2, 3, 4, 5. Right? That 0 is to the right of digits after the decimal point. So we think it's exactly 17.510. Right? It was a really exact measuring device. Okay, so that's that rule. Next one. Zeros between digits are significant. That just means it's part of the number. Right? 0 between digits is like 806. Right? I wouldn't put a 0 in there if it didn't mean something. Just part of the number. Okay, so how many sig figs do I see here? 3, right? The 0 in between digits is just part of the number. Okay? How many sig figs there? 1, 2, 3, 4, 5. Right? This 0 is just part of the number. Part of the number, this is to the right of digits after the decimal point. Does that make sense? All right, good. Zeros to the left of digits before they start, you can put that little extra in there if you want. To the left of digits before they start are non-significant. They are what we consider placeholders. They are non-significant. And let me show you why that is. Okay? Those digits are non-significant because let's say this was measured in like meters. If it was 0.0860 meters, I should just measure it in centimeters instead. Right? I should just say it's 8.60 centimeters, right? I should just change my unit. Rather than have those zeros there, they're not doing anything for me. They're just showing me how small the number is. I should change my unit. Okay, so zeros to the left of digits before they start are non-significant. So both of those, regardless of if they are before or after the decimal point, if they are before digits start, they are non-significant. Okay, so these two are non-significant, which means I have 3 significant figures. Right, 8, 6, and the 0 at the end, because this tells us we think it's exactly 860. Okay, does that part make sense? They are placeholders. I should change my unit if I have numbers that small. Okay. Last one here. All digits used, and I want you to really see, it should really read all visible digits. I'll kind of rewrite that. Put a little extra in here. All visible digits in scientific notation are significant. All visible digits. And so what that means is 2.5 times 10 to the 4th has how many significant figures? Nope, just visible digits. 2.5. Just 2. Right? The times 10 to the 4th is not considered a visible digit, right? That's just part of the scientific notation. If I was going to look at the whole number, it would be this. Right? I don't care about the expanded number. I only care about the ones that are visible to me in scientific notation. So that has 2 sig figs. So scientific notation allows us to express really big and really small numbers in a certain number of significant figures. Okay, if I need to only have 2 sig figs, I can put it in scientific notation and make that work. Okay? Questions about these rules? Okay, the worst one's yet to come. There are some digits, some numbers that are what we consider ambiguous, which means we don't know how many significant figures there are. These are very specific cases that are ambiguous. Okay? Ambiguous numbers have what we call, or what I call, I think I made up this term, but what I call trailing zeros. I don't know if zeros has an E on it, but whatever. Okay? They have trailing zeros. See how these guys right here? Those are what I would consider trailing zeros. They don't have a decimal place. So we don't have any idea how exact that measurement is. That measurement could be 119,500 and we round it up. That could be 120,000.000 and we don't know. So if I would ask you how many significant figures are in that measurement, you would just write, it's ambiguous. Right? That's it. You can't even answer the question. You can't tell me how many are in here because you don't know. Right? So anytime a number has what we call trailing zeros, it is an ambiguous number. We can't tell how many significant figures are in that measurement. Okay, we just don't know. So examples of ambiguous numbers: 80, 150, 4,000, right? Those don't have decimal places. They all end in zeros. Okay, those are all ambiguous numbers. Does that make sense? Let's try a couple here. I don't want to talk about that. Okay. The way that we fix ambiguous numbers is we use scientific notation or we add a decimal place. Okay, so let's say that I wanted to express 120,000 in 3 significant figures. I wanted 120,000 into 3 Sig Figs. So can I add a decimal place and a 0 and that be 3 significant figures? So if I do this, 120,000.0, is that 3 Sig Figs? 1, 2, 3, 4, 5, 6, 7. These zeros are between digits. This one's significant. It's after the decimal place to the right. So that's 7 Sig Figs. Does that work with what I wanted? I have to put it into scientific notation. If I'm only allowed 3 significant figures, I have to do 1.2 what? 0 times 10 to the 1, 2, 3, 4, 5. Okay, does that make sense how I fixed the ambiguous number? Okay, if I wanted 4 Sig Figs, I would add a 0. If I wanted 5 Sig Figs, I could add another 0, right? You can adjust scientific notation to however many you need, from 1 to whatever. Okay, significant figures. Scientific notation gives you the flexibility to adjust that. Okay? Questions with that? All right, let's try, no, before we get to that, let's try identifying a couple more. If I have the number, how many Sig Figs? Don't say it yet, don't say it. Think about it. I want you to hold up your hand. How many Sig Figs do we have? It can't be more than 5 because you only got 5 fingers on your hand. Hold it up, 1, 2, 3, hold it up. I don't care what your number is, but I want to know what your guess is. 1, 2, 3, 4. 4 should have been our number. These are both to the left of digits before they start. Right? Left of digits before they start. So only 4 Sig Figs. These guys are no good. Okay? 4. Okay? How many Sig Figs? 3. Right? This is not ambiguous. Some people get confused and think all whole numbers are ambiguous. Not the case. This has 1, 2, 3 Sig Figs. Right? This 0 is between digits. It's just part of the number. Okay? You could say it out loud because it's more than fingers you have. How many? 1, 2, 3. Say it out loud. 6. Good. 1, 2, 3, 4, 5, 6. Okay. Last one I want to look at here. How many? 3. Good. 3. Visible digits. 1, 2, 3. I do not care about what it looks like in its expanded form. 1, 2. Okay, that's what it looked like. I don't care about that. Right? That would be ambiguous. 2, 4, 8, 0, 0. That's ambiguous. Right? But by putting it here, it tells us we have 3 significant figures. Okay? All right, now we have to think about how do we do math with significant figures? How do we do math? Okay, because in scientific studies, right, I take these measurements with a certain amount of significant figures, and then I have to do my math to match that preciseness. Okay? To match that preciseness. So here we go. I'm going to give you 2 rules, then we're going to do some examples. When I add or subtract When I add or subtract, I do the math and then I round my answer to the least precise value involved, and I'm going to make a little bit of a stipulation with that, or a clarification. Least precise value involved based on decimal places. So let's look at this group of data I gave. Sorry, I'll give you just one more minute to finish writing it down. Right? Why did I take a measurement with no decimal places and the other ones I had 2 decimal places, right? That's silly. But I have to now pay for that mistake, right? So let's say that I have my least precise measurement has no decimal places. That means my answer cannot have more decimal places than one of my original measurements. Okay, so I do the math. Somebody do that math for me. Do that initial. 48 point something. 48.74 is the raw answer I get when I do the math. Okay? 48.74 centimeters. But here's the problem. One of my measurements was not that exact. It did not have 2 decimal places, which means my answer cannot have 2 decimal places. My answer can have 0 decimal places. So how do I round this answer to make it 0 decimal places? 49 centimeters. Okay? So I do the math, then I round my answer to the fewest decimal places involved. You see how I had to pay for that mistake? Because really, my answer should have been 48.74. But because I took some time off during my first measurement, my final answer cannot be as exact as it should be. Does that make sense? So add and subtract, you're looking at decimal places. That's super important. Then your answer, if this one was 12.00, then it could only have 1 decimal place because that one has 1. Yep. See this last one here only has 1 decimal place. So then I would have to round it to 48.7. And if this one had 2, then my answer could have 2. Okay? Next rule is for multiplication and division. Oops. Okay, we already did an example, so that's fine. Multiplication and division, we do the math, then we round to the same number of Sig Figs as the least precise. I'm going to change the wording on that, actually. Round your answer to the fewest number of Sig Figs. Okay, I'll say it a little more clearly. Do the math, then you round your answer to the fewest number of Sig Figs, not decimal places. Oh, that's, okay, that looks like a hashtag. That means number. Yep. That's like a shorthand for number. So round it to the fewest number of significant figures. Sorry. All right, so let's look at this one. I did the math for you. 2.40 times 12. The raw answer there is 28.8. We need to decide how many significant figures can my answer have.
0.
Why 0? Oh, okay, you guys are looking at decimal places. We need to look at Sig Figs. So this one, this digit has how many significant figures? 3. 12 has 2. So my answer can only have 2 Sig Figs. Right. I need to round it to 29. Why can't I just make it 28? Right. The 8 rounds it up. Right. 28 would be 2 Sig Figs, but it's not rounded correctly. So you have to round it correctly too. Okay. Are we ready to try some other ones? Yeah. Let's try it. Try those two on your own. Try those two on your own. There's one, the first one's multiplication, second one is addition. I would agree. Because I'm multiplying and dividing, so I'm looking at sig figs, not decimals. And this one only has 2 sig figs. So I only get 2 sig figs in my answer. How do I get to that point? Can I just make it like this? How many of you went like that?
No.
No good, right? That is ambiguous. That's going to get you a frowny face on your paper. Okay? Can I do this? Can I just leave it like that?
No.
No. So what's my solution? Good. 3.2 times 10 to the second. Right? Here's where we need our decimal place to be. Here's where it is. So that's 1, 2 places. Why couldn't I leave it like this? 3.1 times 10 to the second. My 9 needs to round that up. Okay? That is really important. So if you got that the first time, raise your hand. Wow. Color me impressed. Okay. All right, good. Second one. Allison, tell me what needs to happen on my second one? Least decimal place. Very good. For addition and subtraction, I look at fewest number of decimal places. So out of my 4 measurements, first, second, third, or fourth, which has the fewest decimals, or which is the least precise? Either 2 or 4, right? They both have 1 decimal place. So how do I get my answer to be 1 decimal place? 26.3 centimeters. Right, that's my final answer. Very good. Questions with math on Sig Figs?